Welcome to module number 4 in our series on artificial intelligence. This one addresses logistic regression specifically. So I wanted to recap the topics of some of our recent modules. In the first, we introduced artificial intelligence, machine learning, and neural networks on a pretty fundamental level. In the second module, we dive deeper into neural networks with a focus on the McCullough-Pitts neuron model, the roles of synapse weights and activation functions. We compared feed-forward and feedback network structures, and we presented some basic neural network characteristics or types, with one example being the transformer. In the last module, number 3, we discussed parametric modeling as well as linear regression. So like most of my modules, I'd like to begin with a quick overview of the topic. So let's talk about logistic regression. While linear regression, the topic of the last module, linear regression attempts to estimate some generic relationship between an input X and an output Y. Logistic regression attempts to estimate the behavior of a system as a binary or multi-class classifier. And we'll come back to those topics in a few minutes. We have discussed them in previous modules, however. For example, let's say we observe the frequency with which Michael Jordan makes a three-pointer at various locations on the basketball court. Logistic regression may learn from these observations, from that information, and estimate the probability that Michael Jordan makes any future three-pointers based on the location where he shoots. We may summarize logistic regression, or the process of logistic regression, in 3 steps. First, we need to define something called a logit. We'll explain again later what that means, but essentially, it's a linear combination of parameters and states. We refer to it as Z. We then apply a logistic function to that logit, Z. And then the third step, which is probably the most complex, is to minimize an objective function that's based on the logistic function from step number 2, with the objective of yielding an optimal or a set of optimal model parameters. Now, step number 3 is easier said than done, and we'll see that for this, we'll be using MATLAB, but there's a lot of complications involved with that. Ideally, these optimal parameters, which we call theta sub OPT, same notation from the previous module, these optimal parameters allow the tuned logistic model to accept inputs and accurately estimate the probability that a corresponding output Y falls within one of multiple categories or classifications. If we go back to the Michael Jordan example, it accepts a location on the court and tells us whether this should be a shot that he makes, being one classification, or misses, being the other classification. We also, in this module, consider an example, pretty simple one, of an animal, a small animal, and its observed behavior to approach a food source or not, based on certain environmental factors, the color of what it's approaching, its size, whether there's movement observed around it, and we're going to apply a logistic regression both by hand as well as in MATLAB in order to try to mimic that behavior, that ideal behavior. So now let's return to the main discussion and begin with a little bit of a comparison between linear and logistic regression. So the last module demonstrated how regression may be applied to a linear parametric model, right? It yields a set of optimal parameters, which we denote as theta sub OPT. This module, however, addresses logistic regression. And in the overview, we already demonstrated some of the differences, right? Logistic regression is quite different from the aforementioned, from linear regression. We cannot simply replace the linear function with a logistic type model and call it a day, because the objectives are different. Logistic regression is tasked with estimating the parameters of a binary or multi-class classifier, one that can both assign an input into one of several predefined classifications or categories, again, make Michael Jordan making the shot or missing it, and define the probability that this classification is correct. So are we 80% sure that Michael Jordan will make that shot, or are we only 10% sure that Michael Jordan will make that shot? Now, let's quickly review the concept of a binary classifier, which we had discussed previously, and then kind of add on to that the concept of a multi-class classifier. Really, the difference is quite simple. Binary classifier, only 2 classifications, 2 categories. Multi-class classifier, more than 2. So the definition of a binary classifier, it's a model or a process that categorizes inputs into one of 2 possible classes. And like I said, for the multi-class, we have more than 2. Now, examples of a binary classifier would be looking at your email and determining whether something is spam versus not spam. It could be an exam, pass versus fail, or the Michael Jordan example, make the shot or not. Now for the multi-class classifier, obviously we need to have more than two classifications, so we could be looking, as an example, at classifying animals as cat, dog, or horse, right? And that could play into image recognition, or we could be trying to recognize digits, let's say perhaps 0 through 9 from handwriting, and classify those. So what output does our binary classifier generate? It generates a single probability of success or failure to which a threshold may be applied. Now, what is that threshold? Let's explain with an example. So let's take our example of spam versus not spam, right? We have some sort of logistic regression. It's trained, it accepts an email, and it tries to tell us whether we're dealing with spam or not. And in this case, or for this input, it estimates the probability of something being spam as 76%. But how do we relay that information to the user? Most people are not interested in probabilities. They want a more concrete answer, yes or no, this is spam. So one way to simplify that answer is to use a threshold. If we set a threshold of classification at 75%, then anything whose probability of being spam is higher than that would simply be deemed as yes, it is spam. And that would allow us to take the probability and relay it to the user in a simplified form. Now we could easily increase this threshold to 80%, and in that case, the same probability would yield an answer of no, it's not spam. So we can see there's a lot of nuance in the way that this method can be implemented. Now, if we take a look at the multi-class classifier, the output would be a little bit different. We would receive or get a number of probability values, quantifying the likelihoods for each classification, to which a number of thresholds may be applied. So let's say our tool is taking a look at a picture and it generates the following probabilities: 81% probability that something is a cat, 77% probability that something is a dog, and 10% probability that something is a horse. If again we set a threshold at 75%, then we would have multiple valid classifications. It could be showing up as a cat or a dog. In the same vein, if we increased our threshold to 80%, then we would get no valid classification. So there's a lot of nuance, not only in the way that we perform the logistic regression, but also in the way that we interpret the results. So let's take a look at the components of a logistic regression. The first is the input or the input array, right? That describes the inputs employed for decision making. We can assume that X is an array, and the superscript K simply just tells us which training sample we're dealing with. Classification, I use gamma, the Greek symbol gamma, to refer to that. It tells us which one of the two or more predefined categories to which an input may be assigned. So if we're taking a look at the Michael Jordan example, right, gamma equals 1 would be he makes the shot, and gamma equals 0 would be he misses the shot. Or if we take a look at the cat, dog, and horse example from the previous slide, we would have 3 gamma values. Perhaps the cat would be gamma equals 1, the dog would be gamma equals 2, and the horse would be gamma equals 3. The third component is an ideal probability that a given input X should or should not be assigned to a classification gamma. Now, for a system or for training data that doesn't exhibit stochastic or probabilistic behavior, these probability values should take on either a 0 or a 1 because there's a high level of certainty in that behavior. The fourth component is an ideal output, which we refer to as Y sub IDE. This represents the ideal classification that should be assigned to a given input. Now, for systems with stochastic behavior or probabilistic behavior, this output may be defined by the classification for which the probability is maximum. In other words, there may not be a single clear answer. The ideal result may include some uncertainty within it. Now, there are 2 more components that we need to discuss. Like the ideal probability and ideal output, we also have an estimated probability and an estimated output. So the estimated probability or estimated probability function, represented by G, estimates and or approximates the probability that an input X should be assigned to a classification gamma. So obviously you would expect G to approximate P. Now the estimated output, which we refer to as Y sub EST, estimates or approximates the corresponding classification. And again, for a well-trained system, we expect YEST to be very close to YIDE or to match it. So let's take a look at some expressions relevant to logistic regression. Here we have a function G that estimates the probability that an input is associated with a given classification, and it should be approximately equal to its ideal value. let's go through and explain what each piece means. G represents the function that estimates the probability. Gamma represents the category or classification that we're focusing on. If we remember, right, G estimates the probability that an input should be assigned to a given classification, and so we need to clearly state what classification that is. Are we trying to estimate the probability that Michael Jordan makes the shot, or are we trying to estimate the probability that Michael Jordan misses the shot? So here we have our input, which is the input to the system, and the superscript K is simply telling us which input or which sample we're dealing with. Now this should be approximately equal to the ideal probability. And so what's going on here in the middle? It's simply just saying the probability that the ideal output is equal to the category that we defined for a given input. So over here on the right-hand side is just the ideal probability. So let's take a look at the second expression, which estimates the output, y sub est. And right, this value should be a scalar that represents one of the valid gamma values, one of the valid classifications. So what it says is that if we maximize the estimated probability function with respect to gamma, or we find the gamma value that maximizes the estimated probability, we take the argument from that function, which is gamma, and assign it to y sub est. So we take the probability function, we evaluate it for all the valid gamma functions, all the valid categories or classifications, and the one that's maximum is then assigned as the estimated classification or category. Now there are alternative ways to estimate this output, such as methods based on thresholds. This is similar to what we talked about 1 or 2 slides back. However, this method here is very popular, especially for multi-class classification. Why? Because we do want to provide the user with a single output classification or category normally. It can be confusing to tell the user your input doesn't associate with any categories or it associates with more than one. Okay, so the easiest, or let's say the most straightforward way to do that, as shown right here, is simply to look at the array of all the probabilities associated with all the classifications and pick the one with the maximum value. So far, we have discussed how to estimate the probability that an input is associated with a category, and we have discussed how to estimate that output, or how to take that probability and turn it into a classification. But there's one question that remains, and that is, how do we approximate these values right here? How do we estimate these probabilities? And the key to that is going to be coming up with a set of optimal parameters for this model. Because the optimal parameters, and I know I've drawn on this slide a whole lot, the optimal parameters are the ones that facilitate this pseudo-equivalency between our estimation function g and the true probability p. So let's answer that question. How do we approximate the ideal probability p, or the ideal probability that an input is associated with a given category? Now, one potential approach is to use a linear regression, as shown down here. That would simply be the product of some parameters and some inputs, x. And this yields a scalar output that we would refer to as the logit, z. There is a problem with this, however. The z output, right, the combination of the coefficients and the inputs as a sum, that would be unbounded, unlike a probability, which always needs to take on a value between 0 and 100. And so we can see an example of that expression down below. Note that we associate both z and theta with a classification gamma via superscript. So if you look at this expression down here, it looks a little bit complex, but all it's saying is that a logit for input sample k and category gamma is generated as the product of theta, which is our parameter array for a given classification, as well as the inputs associated with a given sample. And in the middle here, we simply just expand that sum. And again, right, the index k identifies the specific training data sample. But this is problematic. We can't use this as is because this value is not bounded. Now, one solution to this bounding problem is to map the logit, z, to a probability-like bounded value by applying a logistic function to it. And so down here, we see some examples of the type of sigmoid or logistic function that we are going to use. So a quick review of some notation before we jump back into discussing the use of the logistic function. Like the previous module, our parameter array theta is going to be covariant or row-oriented, as shown down here. Our input array x is going to be contravariant or column-oriented, as shown down here. And so their product may be denoted as theta times x, and that would generate a scalar output. Okay, now note here that x superscript k can contain multiple elements, right? Because we can have multiple substates or values included within xk, and they would be multiplied by the parameters. So one would expect, not only expect, but need for the number of elements within x superscript k to be equal to the number of parameters. And again, here you can see this expression expanded. I can spend a quick second explaining it. Again, you have the parameters associated with a given classification, where the classification is the superscript. The subscript here, right, that tells us what parameter number it is. Then we have the state x, the input associated with a given sample. And then you have 1, 2, 3, all the way down to nx, where the second superscript bracket, that tells you which input you're dealing with. Now, what's this 1 right here? If you remember, we used something similar in the linear regression, right? This 1 serves as the coefficient for the 0th parameter, which essentially serves as our constant offset. And then over here, you can see the whole expression expanded. Again, note that contravariant or row indices are represented by bracketed superscripts, right? You can see those here, while covariant or column indices are represented by bracketed subscripts. Now here is an example of a training data array. I kind of expanded it a little bit. And what we see is that we expect it to be a rank 2 algebraic object. Rank 2 meaning that there are 2 different indices required to index a single element. So if we take x here, we can split it up into multiple training samples, or multiple samples, because they don't have to be training, multiple samples. X superscript 1, x superscript 2, all the way to x superscript nt, where nt represents the number of training samples, or I could just say number of samples we have available, because we could be using this for inference or for testing. Now, as shown in the red, right, this single input can then be decomposed into multiple elements, where we expect to see, going back to here, we expect to see a structure that looks like this. So we have x superscript 1, indicating it's the first training sample. We have our 0th element, all the way down to x superscript 1, again still for the first training sample, but element n sub x, where n sub x represents the number of input elements or substates associated with a single sample. We can do the same thing for the blue. Right, the first superscript is always a 2, indicating that it's associated with the second sample. And again, 0, 1, 2, 3, all the way down to n sub x. And then down here, we do the same thing for the final sample, x superscript nt, telling us that it's associated with the final training sample or the final sample. And then 0, 1, 2, all the way down to nx. So the size of this algebraic object should be, right, it has 2 contravariant sizes. Okay, we have a length along 2 contravariant ranks. The length along the first rank is n sub t, which is the number of samples or number of training samples. And then the second is nx plus 1. And the reason for that is because we start off with the 0th element instead of the first. So the number of parameters is really 1 more than the number of states, assuming that we don't count this, this number 1 here as an input state. And so I just wanted to review this so when we get to the example, you're aware of what, at least from my implementation, what the input or the training input should look like. So we still haven't answered the question of how we can apply a logistic function to our logit z. Now this is achieved by a functional mapping like that shown below, and it takes the unbounded logit value and generates a bounded value between 0 and 1 or 0 and 100%. Now the function again is g, with a superscript gamma that represents the classification we are interested in. It accepts an input x, and we use the k superscript to indicate which sample we're concerned with. And the mapping is pretty straightforward. The numerator is e to the z, or e to the product of theta times x, over 1 plus e to the z, or e to the power of theta times x, and over here we just have an alternate representation of that. Now for this type of binary classification, there are 2 probability mapping functions that exist. Essentially, we only have 2 cases. Yes, the input is associated with category gamma, or no, it's not, which by default means it's associated with the other category. And so what we see here is that g with a superscript of gamma represents the yes, and g with a superscript of not gamma represents the no. This probability should be equal to 100% minus the probability of yes, right? The probability of no equals 100% minus the probability of yes. So the total probability of this plus this must equal 100%. So now we can elaborate on those functions in greater detail. Looking at this slide now, I probably would have called this class 1 and this class 0 corresponding to yes and no. However, we'll leave it the way it is for right now. So the estimated probability that an input belongs to class 0, which I'm going to call the yes or the positive output, again, I know it's a little bit counterintuitive, uses the same mapping from the previous slide, e to the theta x over 1 plus e to the theta x. Okay, and this should be approximately equal to that ideal probability that the ideal solution is equal to the category gamma, which in this case, that is A0, for the given input x superscript k. Now we know that the other classification, which is no in this case, where I guess counterintuitively 1 equals no, right? The probability of this is equivalent to the not gamma, is 1 minus this probability up here. Now, I'm not going to go into all this math, but essentially the result that we end up with is e to the negative theta 0. So note here that we're trying to define the probability of a classification of 1, but we use the theta values associated with 0. And what this does is this allows us to define both probabilities in terms of a single set of parameters. So negative theta superscript 0 times the input plus 1 e to the negative theta superscript 0 x superscript k. So this expression generates or estimates the probability that the ideal output is equal to 0, and this down here generates the probability that the ideal output equals 1, again, for a given input. But more times than not, we don't really need to use this expression, because if we have the probabilities up here, right, we would simply use the 1 minus in order to estimate the probabilities for the other classification. Again, don't forget about these references that I put up here in the top right-hand corner. They're very interesting, and I encourage you to check them out. So what have we learned so far? A little bit of a recap here. Logistic regression is tasked with classification, and the model employed by logistic regression estimates the probability that an input, which we've been calling x superscript k, should be associated with a given classification that we've predominantly been using gamma to represent. It's based on patterns established by the training data, where the training data is essentially the collection of the inputs and their associated ideal outputs. It may also apply a threshold or maximization to estimate the ideal classification associated with that input. So the logistic regression should give us an estimation of the probability that an input belongs to a category, as well as some estimated category value. And again, we've already talked about how we can use a threshold or a maximization in order to take this G and turn it into an estimated category. Now, with regard to training, both linear and logistic regressions attempt to accurately define the parameters of a linear-like model. Okay, they both start off with a linear-like model. However, for logistic regression, this linear model is enveloped or contained within a logic to probability mapping, which is what we showed right here as well as right here. Now, we still haven't talked about how to solve this. How do we come up with the optimal parameters? So, unfortunately, for this type of logistic regression, there's no closed form solution. We can't use this expression from the previous module where we simply calculate the optimal parameter array using some basic linear algebra. And this is because of the logistic function's nonlinear nature. This logistic regression may be solved via minimization as shown below. Okay, so the optimal parameters, theta sub OPT, that minimize this function are expected to also provide the best and most accurate classification. So if we have our function g for a given category, right, and we feed to it some input, and then now I'm also going to add a second input, which is the theta values, right? If we supply the optimal theta values, then we expect for this to be approximately or very accurately represent the ideal probability P. And so the quality of this relationship right here is dependent on the optimality or the quality of those parameters or of the parameter array. So now let's dive in to this expression. So what we see is that the optimal parameter set for category gamma is equal to the arguments, where the arguments are the theta values, that minimize this function right here. Now this function is the average, right? Because 1 over the number of training samples, or the number of samples, we sum these together, for a number of functions, which I'm going to simply call f natural log, and then I'm going to give it a k value. So natural log of 1 plus e to the, and we should know what all three of these values are, right? The ideal value associated with the current k, the parameters, which are independent of k, right? These parameters don't change from element to element of this sum, and then the input associated with index k. So we take the product of those three. We expect to have nt elements within that sum. We average them all together, and then we try to find those values of theta, the theta parameter array that minimizes all of this, and that would be our optimal parameter set. Now, like I think I said earlier, that's easier said than done. And we are not going to, at least not in this module, present a straightforward way of performing that minimization. We're going to rely on MATLAB in order to do that. That being said, you can do this by hand. And, the topic of nonlinear system analysis is something that I hope to get to in future modules. So let's take a look at an example. All right, so consider some animal, and it has an instinct to collect small red berries and avoid predators. Pretty realistic, practical set of objectives for this small animal. So it's conditioned to approach an object which it thinks may be food under the following conditions. So if the object is small and it doesn't detect any local movement, thumbs up, move towards the object. If the object is red and the animal doesn't detect any local movement, thumbs up, head towards the object. And then if the object is both small and red, the animal really doesn't care whether it detects any movement. It's going to go ahead and try to pursue that food. Now we can decompose this instinct into three observations or inputs. So the first is the object small? Yes or no? And so we're going to refer to that as the first input. Is the object red? Yes or no? That's the second. And is the object moving, or should I have said, is the environment moving, or is there something moving in that area? Yes or no? Now this first one right here, so I said there's three observations, but there will be four parameters. If you remember, we talked about this previously, how the x always has a value of 1 to begin with, because that serves as the coefficient for theta sub 0, and essentially is the offset for the regression. So the x array has 4 elements, although there's really only 3 distinct observations with this, again, facilitating an offset. All right, so the animal's brain must practically generate a single output. It must tell the animal, yes or no, do you approach the object? We are going to have training data with an ideal answer there, and we are going to use our logistic regression in order to mimic that and predict, based on inputs, whether it should, yes or no, pursue this source of food. Our objective in this example is to employ logistic regression to estimate the optimal parameters for our logistic model, such that this model accurately represents the behavior described below. And so this table is simply just a summary, a representation of what we discussed in the previous slide. Okay, you have, is the object small, is the object red, and is the environment moving? So to take a look at one example, right, let's take a look at this row right here. If something is small and red, it doesn't matter whether you have movement or not. In both cases, and this is the Y ideal, in both cases, the animal is trained, instinctually, will go after the food. Now, to take a look at an alternative case, let's take a look at this row. If it sees something that is, actually, let's take a look at this row down here. If it sees something that is red, but not small, and it detects movement, then in that case, it's not going after the food, and this fits with what we said up here. So pretty simple example. I know it's a little bit elementary, but really it provides a good base case for us to test our knowledge of logistic regression. So what are the steps here? The first step is going to be really practical. We need to define an algebraic object to store all of our training data. So initially, I was going to use a structure like this, where you see each row corresponds to a training data sample, and it has 2 parts. On the left, we have the inputs, and on the right, we have the outputs. Now, the input is going to have a length, a contravariant length of 4, right? Because there's 3 inputs plus the additional offset. And the output is a single scalar value. And we do this for all the rows. So a rank 2 object. Now, the problem with this is it's a little bit difficult to represent X as a column array embedded within a column array in MATLAB. So what if we just take all 3 of these and we just transpose them and lay them on their belly? And that yields something that looks like this, which is a traditional, matrix with, nt number of rows and 5 columns, where I guess it would be nx plus 1 for the number of the elements within X, and then you also have the Y value. And so this is something that MATLAB can store as a single 2D matrix. So although this is the better representation of the training data, we're going to go ahead and use this representation right here. And lastly, for some parts of the equation, it's easier if we have a quick way to denote X versus its transpose. So here is X, and here is X sub t, which is not the transpose of the whole thing. It's simply just the transpose of the individual rows. So if you see this value in the equation later on, that's what it's referring to. All right, now we are going to solve this using MATLAB, and so as we go through the various steps, I'll show you the associated code. This is simply us declaring the training data as one would expect. We have 1, 2, 3, 4, 5, 6, 7, 8 rows, and these 4 columns denote X subscript t, and then the last column would be the Y ideal. So step number 2 requires us to define symbolic parameters for a model that correspond to a positive outcome. Now we could run this logistic regression in terms of gamma equals 1 or gamma equals 0, right? The probability that the animal pursues the food or the probability that the animal doesn't pursue the food. We are assuming for this kind of binary classification that the sum of those 2 probabilities equals 100%. So either one is fine. I'm going to go ahead and use the positive outcome. So we are going to be looking to define parameters that estimate the probability that an input is associated with yes, it pursues the food. And so that's why you see the blue superscript here is a 1 for all of these parameters. Again, indicating these parameters allow us to estimate the probability that yes, the animal pursues the food. And it has a covariant length along its only covariant rank of nx plus 1 equals 4, right? Because we really only have 3 inputs plus the offset equals 4. Right, the number of parameters, which is actually 4, exceeds the number of input substates or input elements by 1, like I said, resulting in a parameter array with length 4. Remember that our solution requires minimization of a function that sums multiple natural log functions. So we've already seen this before. This is our solution method. I put it back up on the screen because I wanted to remind us of the name of these subfunctions, or the name that I assigned to them. So each one of these elements is going to be referred to as f subscript ln with a superscript of k, which indicates the training sample it deals with. So if we were to look at this down here, we have 1 over nt, the sum from k equals 1 to nt of natural log k, right? That's the same as what we have up above. Because when we demonstrate how to physically implement this method, it's going to be easier for us to use these functional representations as opposed to having to, use this equation every single time. So step number 3 is to define the natural log subfunctions, again, right, these guys that we just talked about, that's an L, for all 8 training data samples. So here is an example for the first. K equals 1, we're dealing with the first training sample, natural log of 1 plus e to the ideal solution, y sub IDE for k equals 1, right? What's the ideal solution associated with the first training sample, times our parameter array times the inputs associated with the first training sample. So this is a scalar value. This is going to be a row-oriented array, and this is going to be a column-oriented array. I know that we transposed it, but you can see right here I actually untransposed it. So what we end up, again, natural log 1 plus e to the, now for the first training sample, that's where all 3 of the inputs are 0. Something's not small, it's not red, and there's nothing moving. The animal's not going to pursue that, so that's a 0. Here we have our parameter array, and here we have our inputs. It's not small, it's not red, it's not moving. Remember, this 1 is always present as the coefficient for the offset. Now here we have some more examples. I didn't show all 8 on the screen because That would have been a little bit tedious, and it also would have made the equations pretty small, but there's really not too much differentiation between each row. So here we have the natural log subfunction for k equals 1, k equals 2, k equals 3, k equals 4, and we would need 8 of those. Now we can see here this is the ideal solution for the first, for the second, for the third. So the third row is the first one where ideally the animal goes after the food and then it goes back to 0. Here you can see the inputs. So here it's not red, it's not small, we don't see any movement. Here it's not red, it's not small, and it does see movement. Here it's not red, but it is small, and it doesn't see any movement, and then etc. You can keep going down. Now, if we look at the red, the blue, and the green, where the red, right, represents the ideal outputs, the blue represents the parameters, and the green represents the inputs, we see that the ideal output values change with the training data sample as we go down. The input values also change with the training input or training data sample. But for the blue, right, the same parameters are used for every natural log subfunction. And the reason for that is we're only trying to generate one set of optimal parameters. And so we want to use the same set of parameters, symbolic parameters, for every row or for every element of this sum. Now let's take a look at the MATLAB that we used. So this is the second piece of that script. What I did was I defined symbolic variables corresponding to the 4 parameters, theta 0, theta 1, theta 2, theta 3, and then I compiled all those together into an array. Then I created a function, which I called function log. Okay, it is a function of the symbolic array, which we called array theta, and each one is natural log. Remember that MATLAB uses the symbol log 10 for log base 10, and log denotes natural log, actually. A little bit confusing. And then we use the equation that we had defined previously, 1 plus e to the y ideal times theta times x. And all we do is increment which row of this we call each time. And again, note that this apostrophe right here is equivalent to untransposing the input data array as needed in order to make this multiplication here work out. So we have the function, or most of the function, that we want to minimize. Now we need to minimize it with respect to our parameter array. Now, we are not going to attempt to minimize this function by hand. It requires a separate lecture on nonlinear system optimization. However, we can use MATLAB to do so. So again, the optimal parameters associated with category 1, those would be the arguments, theta, that minimize this function right here. Now we've done all this work, right? We've created this sum of all the different natural log functions with respect to k. That's what all of this is right here. So now all we need to do is to tell MATLAB in order to minimize it. And right, I think I already showed this, right? We can redefine this function in terms of those natural log subfunctions that there's 8 of. Now here is the MATLAB code that performs the minimization. You can use this QR code up here if you'd like to download the whole thing. Now you may ask, why is this in a for loop? We really only need to run this minimization once. And the reason for that is essentially it didn't work every time. We do have to set initial conditions for the minimization, and it didn't always converge. So my quick and dirty solution was to essentially run the minimization 1,000 times with randomly generated initial conditions until it gave me a solution I liked. Okay, so within the loop, there's several steps. The first is to initialize our parameters, and I randomly initialize them. And then this is really the most important line right here, which is to apply the minimization. So the command is fminsearch. We supply to it the function that we want to minimize, which we defined previously as fun logarithmic, as well as the initial conditions of the parameters we're trying to minimize. Now, so how does fminsearch know with respect to what variables the minimization is being performed? If you go all the way back here, we essentially define the function in terms of array theta, and that's how fminsearch knows that it's trying to generate optimal values of array theta. And then this piece down here, all we're really doing is calculating the probabilities of yes or no. I mean, I guess I really only needed one, but I did it for both, yes or no. And this employs an equation that we defined previously in the lecture. Then right here, I define or I calculate the difference between the estimated and the ideal categories. And then I simply check to see if they match relatively well. Then I break the loop and exit. So we don't always run through all 1,000 trials. Essentially, when we get an answer that works, we go ahead and break the loop. So we randomly initialize theta, and there's probably better ways to do that. I used a random initialization just because this is something we're doing for a lecture. We perform the initialization and run the minimization, and then we have to use those optimal parameters. Right, this is the optimal parameters, and we have to use those to calculate the probabilities, and then we can compare those probabilities and the resulting classifications to the ideal that was included in the training data. Okay, so after minimization, this is kind of picking up about halfway through the MATLAB, right? We take the optimal parameters and we plug them into our probability estimation function in order to give us the resultant probabilities. Okay, and what we have to do, if we want to get 8 probabilities, we need to run this expression 8 times, but each one of the 8 uses the same set of optimal parameters. You've seen this equation before. If we want to generate or estimate the probability that x superscript k is or should be assigned to classification 1, what we do is we calculate e to the theta opt times its corresponding input over 1 plus e to the theta opt times x. And this is why it's important to perform the minimization, right? Because this function doesn't work unless these parameters are optimal. And then after we do that 8 times, 1, 2, 3, 4, 5, 6, 7, 8, we should end up, we do end up with 8 probabilities that tell us whether, yes or no, the animal should approach the food. So in this slide, I compiled all the values into a single algebraic object. We have our inputs, we have our ideal outputs, and we have our estimated outputs. Now, to be more accurate, this is really not the estimated output, which should be a classification, either 0 or 1. Really, the green column contains g of x, or what's the probability that the input corresponds to yes, going after the food. But because this is a non-probabilistic, non-stochastic system, meaning that every input always corresponds to the same ideal output, these values here in the blue can be looked at as probabilities, either 0% no, don't go after the food, or 100% yes, do go after the food. So a comparison of the blue and the green kind of works. Now what we see is that the results are very positive. Okay, matching 0, 0, matching 0, 0, matching 1, 1. So both the estimated and the ideal outputs say the same thing. For these inputs, it should not go after the food. For these inputs, it should not go after the food. For these inputs, it should go after the food. Now, there are a couple of small discrepancies, right? For the fourth line, we get a less than 1% chance that the animal should go after the food, which is pretty close to the ideal. And then down here, we have about a 1.2% chance that the animal should go after the food, which ideally, that should be 0. I'm sure if I played around with this optimization a little bit and with the MATLAB code, perhaps with the initial conditions, I could have got a closer match. But I think this is a very positive result that demonstrates how the logistic regression works, right? How it took the relationship between the inputs and the ideal outputs and mimicked that to generate these estimated values. So let's summarize what we talked about in this module. We first discussed the overall objective of logistic regression, which is to predict classification probabilities based on training data. If we go back to the Michael Jordan example from the beginning, what we saw was, we could observe Michael Jordan shoot 3-pointers at various points on the court, and we can use that as training data. The inputs would be the location that he shot, and the ideal output would be whether he makes the shot or not. And then we can try to mimic those patterns using logistic regression. Now, we define several expressions, one being the logit z, which is essentially a linear combination of our parameters and our inputs, but that isn't sufficient for this purpose because it generates an unbounded output, and we need a probability between 0 and 100. So what we did was apply to that the logistic function, which then bounded the output between 0 and 1, or 0 and 100%. And this helped us to generate our probability estimation function, which we call g, and so that tells us the probability that an input x should be or belongs to a classification that we can denote as gamma. Now we have to solve this logistic regression via minimization, and we looked at exactly what expression needs to be minimized, and then we moved on to our binary classifier example, the one with the small animal. We were looking at whether it should pursue food or not. It employed 8 training data samples, 4 different parameters, and essentially we solved that by hand as well as via MATLAB. And I think that was a really good demonstration of how to implement the logistic regression for a binary classifier, and it should be relatively easy to extrapolate that to a multi-class classifier. So I would like to supply all of you a homework exercise to do at home to test the skills that you've learned in this module. If you're able to solve it, please submit your solution in the comment section below. You can submit the final answer only, or if YouTube will let you, you can submit the code or perhaps a link to GitHub or Dropbox that allows others to view the code. Once I get enough responses, I will go ahead and submit or post my solution as well. So what is this homework problem? I want you to consider a traditional OR gate employed by Boolean logic, and I want you to apply a logistic regression to that data set, essentially the inputs to a OR gate as well as the outputs. And if you want to get fancy, you could try that with an OR gate with more than 2 inputs. Now this should yield, like all of our work here in this module, this should yield an optimal set of parameters, theta sub OPT, that predict whether the OR gate should generate a positive output of 1 or a negative output of 0. So this is a little bit simpler than the example that we looked at in this module, but still I think is a really good opportunity for you to adapt our example, our code, and apply it to a different system. So before we close this module, I did want to briefly introduce the next. The topic of the next module is machine learning, error correction, and then the perceptron. I know we've already talked about those in some level of detail previously, but now we're going to really do a deep dive. Now, one interesting thing is we're going to reuse the same example from this module in the next, right? The small animal that's trying to decide whether it should pursue food or not, but we're going to use a more formal machine learning approach. Specifically, we're going to be using a single layer perceptron, and we're going to code that in MATLAB and compare the solution from this module to that, that we're going to generate in the next. Now, even more interesting, if we look 2 modules ahead, we're going to start using Python and PyTorch, which are more widely accepted tools for this type of machine learning work. So we're going to take the MATLAB code from the next module, translate that to Python and PyTorch, and use that 2 modules ahead, which I think will be a really interesting goal to work toward.